Okay, everybody, so now we've got ourselves confidence intervals for single proportions. Awesome. You can make confidence intervals for any number of statistics, in any number of those numbers of statistics. So one proportion, two proportions, one mean, two means. We're only going to have time in this class to do one proportion and then next week one mean, but that's okay. You can form more. It's all about the same thing. It's a statistic plus or minus a margin of error. That's every confidence interval. The trick is figuring out how to calculate the statistic and then figuring out how to calculate the margin of error. Okay, now, what I want to look at in this first video of this playlist is if you get a statistically significant result from your interval in your research, what does that tell you? So, for example, yesterday, or whatever day you watch the videos, we looked at 23,000 some spins of pennies and discovered that when you spin a penny, you end up getting heads less than when you flip a penny. And the 95% confidence interval for the percent of times we actually get heads on a spun penny, we calculated to be between 43% and 45%. That's over tens of thousands of trials. Now, I call that a statistically significant result because when we went into that, we were expecting a proportion of 50%. 0.5, let me write it as 50% since I wrote those as percentages. We were expecting this, but we got that. That is statistically significantly different than this because 50% is not within that range. If you remember, p hat for our very, very large sample was 44%. Even with the margin of error of just about 1%, 50% is still not in this range. Awesome. So at that point, you can feel 95% confident and say there is a statistically significant difference between spinning a penny and looking at heads and flipping a penny and looking at heads. Now, we have to ask ourselves, how do we measure that difference? So there is a statistically significant difference. How is it measured? Now, in all the years I've done stats for people on their PhDs or in their own classes, there have been two main measures that I have seen used, and I want to share those with you in this video. Okay, first thing I'm going to do though is I'm going to clear this board and get us some room to work. Okay, so you've run your confidence interval and you are surprised because you learned something. You learned that there is a statistically significant difference between spinning a penny and flipping a penny. Now, you can stop there. Or you can say, how different is it? In all the years I have done research stats with folks, I have found two measures that are very, very commonly used. There are many measures that are used, but two that I keep seeing over and over and over again. One is called the minimum detectable difference. We'll do that one first. The minimum detectable difference, better known as MDD. MDD. Okay. That's what you'll often see in papers. What this does is it finds the difference between the expected value that you're looking for, or you're expecting. You're expecting 50%. If you anything with a coin, you're expecting a percentage of 50%. But our sample came up at 44%. But with the margin of error, it actually came up between 43 and 45%. Now, we don't know for 100% certain where the true population proportion of spinning heads is. We are just statistically confident it's in this range somewhere. What is the minimum difference between this range and the expected value of 50%? Well, if you imagine this thing on a number line with 50% over here, and let's just put, let's see, let's get on a 43, we'll go 40 here, 40%, 45% here, okay? This interval goes between 43 and 45%. Minimally, 50% is here. Minimally, there's a 5% difference. Maximally, there's a 7% difference. But maximal detectable difference isn't used. You want to go on the conservative side. You want to say, okay, I know I'm not 100% certain about this interval, but I'm confident that there's at least a difference of 5%. So what minimum measurable difference is, it's literally the minimum distance between your confidence interval and the expected proportion that was actually predicted from the result of the study. You can only do this if the interval doesn't touch that expected proportion. If the proportion ends up in the interval, then there's no statistically significant thing to talk about. Nothing interesting happened. But something interesting happened here. And minimally, we do the 50% minus that 45% to get 5%. Now, you can also subtract them the other way and give it a minus 5%, because that gives you also the direction. So if you were to do, in this way, I did P, I'm not even going to write it with letters because it's going to be too confusing. It's expected minus end of confidence interval. If you do it the other way, in this case, you'd get a negative number, which would then let the reader know that this is below this. That doesn't always happen. Sometimes you're expecting a percentage and it comes out above it, in which case. So just communicate that difference to your reader. The big point of this part of the video is the minimum detectable difference is just the smallest possible distance between the expected proportion and the closest side of the confidence interval. Cool. So minimum detectable difference, that's one of two measures I see used very often in research. Let's talk about the other one next. Okay, now the second one is called relative risk, and it's a weird phrase in this context because relative risk is generally used when you're talking about illness, when you're comparing the incidence of a certain disease in a control group, which would be like the 50%, and the experimental group, which would be like the group that got a certain drug. So you're trying to see if maybe a certain drug has any kind of an effect on the incidence of a certain disease. Okay. Relative risk is actually pretty straightforward. It's a division problem. You take your p hat value and you divide it by your expected proportion value. So in this case, you take your 44% and you divide it by 50%, or 0.44 over 0.5, which, if I do that math in my head right, that's going to be 88%. What does that tell us? It tells us that the percentage we got in our sample was 88% of the percentage we were expecting. 44 is 88% of 50. Or it's 12% lower. There's a couple ways you could interpret that percentage. Just a heads up, relative risk calculations sometimes carry their own confidence intervals. You may have noticed that we didn't use the confidence interval for this calculation. That means we lost that margin of error, which means there should be a margin of error included in the relative risk calculation. So that 88% shouldn't just be 88, it should be 88% plus or minus. We're not going to deal with that right now. I think I'm going to put that on your second exam. That'll be a fun little follow-up question for down the pike so we can revisit confidence intervals. But that's relative risk. What happened proportion-wise in your sample divided by what you were expecting, and it's a measure of the percentage efficacy or the percentage risk. And again, risk is tricky in this one. There's no risk in spinning a penny, but very often it's talking about the risk of, say, a certain disease. Okay, so now you've seen two follow-up measures. Assuming you got some statistically significant results from your initial confidence interval, you can go further. Minimum detectable difference is probably the easiest one to kind of understand. Relative risk without a confidence interval is a little bit more, it's a little bit hand wavy because it needs its interval. But for right now, let's just focus on that computation. Okay, that's video one. What I want to do in the next video is show you how you can get a little bit carried away with confidence intervals. We're going to talk about that next.